Hey everyone, welcome back to another video. This will be lesson 4 in the series on abstract algebra. And so in today's lesson, we're going to be talking about group actions. And so to kind of get an introduction to what a group action is, I guess I should admit that I may have lied in an earlier lesson. When I was talking about the group D3, we understood this as the symmetries of a triangle. In actuality, mathematicians think of D3 as an abstract group. It's thought of just the symbols it has and the multiplication law that relates the symbols to one another. Now, what we did was we realized D3 as the symmetries of the triangle. D3 can be realized as symmetries of an equilateral triangle. And that's how we thought of D3. In actuality, this idea of realizing the symmetries of D3 as the symmetries of an equilateral triangle is called a group action. We think of this as D3 acting on the triangle. This symbol means acts on. This is the abstract group. And this equilateral triangle is some set that it acts on. And so you would expect group actions to have certain rules that determine how they behave. So, for example, if I label the vertices of this triangle as V1, V2, and V3, you can think of maybe some rules like, okay, the R in D3, if I try to find how R acts on V1, well, when I do the rotation, V3 takes the place of V1. So I'll say R dot V1 equals V3. This dot is not the same dot as the multiplication inside of the group. It's the group action multiplication law, which we'll discuss more, but it's usually just a handy way of writing how R acts on set elements. And so another example would be R times V2 would be V1, because when you apply R, V1 goes to V2 here. Finally, you could get something like S times V1 equals V1, because if you flip across the middle here, V1 stays the same. So all the elements we think of in D3 can be thought of as acting on the set of the equilateral triangle, which we're thinking of as V1, V2, V3. And so what we thought of as D3 is really the abstract group D3 realized through a group action. So let's figure out what the definition of a group action is. A group action of G on a set X is a map phi from G cross X to X. All this is saying is phi, which I'm thinking of as this dot here, takes an element, a group element, and an element in the set, and then sends it to another element in the set, which we write as, usually just write as G dot X, which satisfies two properties. The first one is that for all G1 and G2 in G and X in X, you get this thing that resembles associativity, where if you first do G2 dot X and then do G1 afterwards, you get the same thing as just doing G1 times G2 and then acting on X. And note that this multiplication inside the parentheses is the group multiplication, but this is the action. Okay, then the second one is we have, for all x and x, 1 dot x equals x. And so you can think this one here obviously meaning the identity in G. And this rule is kind of telling us that, like, you know, we still want the identity to play a similar role as it does in the group, where, like, if it's acting on the set, it shouldn't really do anything to the set elements. And we usually denote if G acts on a group, or if there's a group action, as G acts on X, as I showed before, this little arrow. So just a quick note here. We can think of G as D3 and X as the equilateral triangle for our quick example. Okay, let's introduce some other definitions related to group actions, which are ways of taking group actions and forming sets that may be valuable to analyze, which are called orbits and stabilizers. So let's first define the orbit. So let G act on a set X. The orbit of an element X in X is the set O sub X, that's just how I'm going to denote it, inside of X, where O of X equals those elements that look like G dot X for all G in G. So what this is saying is take an element X in your set and then basically have every element in the group act on that set element and see where it goes. So if I'm looking at D3, I might look at one of the vertices and see where all the rotations and flips send it, and that's my orbit. It's kind of why it's called an orbit. It's like all the places that X can go because of G. Now let's define the stabilizer. Once again, let the group G act on set X. The stabilizer of an element X in X is the subgroup usually denoted stab X, which is a subgroup in G, where stab X equals those G such that we get G dot X equals X. So how you can think of this is like for D3, if I'm looking at my X is like V1 as above here, if I go up here, so if I'm looking at like V1 here, then maybe something that's in the stabilizer is S, because we saw that S dot V1 equals V1. It doesn't change anything. So S would be in the stabilizer of V1. Now I'll leave it up to you to prove that stab X is actually a subgroup for all group elements, but it shouldn't be too difficult to prove. Okay, let's look at a quick example that should hopefully fortify these definitions. So we're going to look at the symmetric group on n like 1 through n. So this is like permutations of the numbers 1 through n. And we're going to have it act on, I guess what's most natural is the set 1 through n. And we're going to define our group action, where for sigma and Sn, and k in 1 through n, you get sigma dot k equals sigma composed with k. So this is just saying if I want to have sigma act on this set element k, just find where sigma sends k as a permutation. So you might have the permutation that sends 1 to 2, 2 to 3, 3 to 4, so on and so forth. That permutation dotted with maybe n equals 1, and with 1 it equals 2, and so on and so forth. Okay, so now that we have this definition of the group action, let's see if we can prove that it follows the group action laws that we defined. So first, let's consider the identity element in Sn, which is that element that sends everything to itself. So we should see we want that 1.k equals k. We get that 1.k equals 1 applied to k, but we know as the identity element sends everything to itself, so 1.k should equal k. Perfect. And that means it satisfies that law. This is for any k from 1 to n. Now let's take sigma 1 and sigma 2 in Sn. What we see is that, of course, k in 1 to n. We see sigma 1 dot sigma 2 dot k is going to equal sigma 1 dot sigma 2 applied to k, which equals sigma 1 of sigma 2 of k. But we also see that sigma 1 dotted sigma 2 acting on k is sigma 1 composed with sigma 2 dotting on k, which just equals the same thing, sigma 1 of sigma 2 of k. And so this then proves our other group action definition requirement. Okay, so we know this is a group action. Let's see if we can identify what the orbits and stabilizers are of some elements. So let's consider like k equals 1 in 1 to n. And we want to find the orbit O of 1. So consider this permutation. In Sn, where we define sigma I to be like this. Sigma I of 1 equals I. Sigma I of I equals 1. Then we get sigma I of k just is going to be equal to k for all k not equal to 1 or I. You can also just think of this as in cyclic notation of swapping 1 and I, and then everything else stays the same. So sigma I is kind of equivalent to this. So we see that if we're looking at the orbit O of 1, sigma 1 dotted with 1 is going to be an O of 1. So is sigma 2 dotted with 1, of course, because these are all group elements, and so on and so forth. So we get like sigma n dotted with 1 is in O1. But we see that sigma 1 dotted with 1 is, well, 1. This is 2, and all the way to this being n. But this implies that 1 through n is, sorry, I should write, it's a subset of O of 1. But we also know that O of 1 as an orbit is a subset of the set X, which is just 1 to n. But this just means that it's got to be equal to 1 through n. So the orbit of 1 here is actually the entire set, which is interesting. If you want to, you can try others, and you might find the same thing, that a lot of them are also going to have the fact that the orbit is the entire set. Now let's look at the stabilizer of 1. So that is those elements in G, such that I should write sigma here, or I should write Sn, just to make my notation consistent. And so it's those sigma and Sn such that sigma of 1, which is sigma dotted with 1, equals 1. So it fixes it. So if you're thinking, when is this the case? Well, let's draw a picture. All the way to n. So I know my sigma needs to send 1 to 1, but it doesn't really care about what happens for 2 through n. In fact, 2 through n, all of these can get sent to basically wherever they want. And so you can think of sigma as keeping one constant, but permuting the set 2 through n. But we kind of know what that's equivalent to. That's just equivalent to Sn minus 1. Because the symmetric group on n minus 1 variables is just equivalent to permuting 2 through n, because there's n minus 1 things here. So we found that the stabilizer of 1 is the subgroup S sub n minus 1 being a subgroup in Sn. Okay, great. So after that example, I'm going to introduce some other definitions, and we're going to work our way through kind of one of the first important theorems that's going to be proven, hopefully in 350 and in this lesson series, which is called Cayley's theorem. And so to build up to that, we're going to introduce some helpful definitions. Some are my own terms, but they're ideas that you should understand nonetheless, even if they're not called the same way I do. So let's define something called the action homomorphism. The action homomorphism of G acting on a set X, so the specific action, is the map rho from G to Sx, where S sub x here is the symmetric group on the set X. What this means is you can think of this as permuting elements of the set X. Permuting is, in a sense, just a bijective function from one to the other. So really, Sx can be thought of as the set of all bijective functions from x to x, where we get that rho of G has to equal some element in here, which I'm going to call sigma sub G. And I need to define what sigma sub G is, where sigma sub G of x, because remember sigma sub G should go from x to x, equals G dot x. And this is for all x in x and G in G. So this seems confusing. I'm going to try to work through it, and the best way to do that is to kind of prove what I'm saying here. And the things we have to prove is, first, we want to prove that sigma G is a permutation of x, and that's equivalent to proving it's a bijective function from x to x. And then we also want to prove that rho is a homomorphism. So I've kind of defined this map, which sends a group element to something you can think of as like a map that kind of tells me how that element acts on the set X. In that, like, sigma G kind of tells me, like, how does G act on every element X and X. And so I first need to prove that this sigma G is really a permutation, which means that this map makes sense. And second of all, that it is a homomorphism as I claim in the title. So let's prove those things. So let's first prove that sigma G is bijective. So let two elements at x and y, and assume that sigma G of x equals sigma G of y. So we're first going to try to prove it's injective, and then surjectivity should be pretty easy. Then we get that g dot x equals g dot y. But if I multiply by g inverse on both sides, or if I have g inverse act on both these items, I get g inverse dotted with g dot x equals g inverse dotted with g dot y. But using the action law, I can regroup the g inverse in g, and this just gets me 1 dot x equals, and I can do the same thing over here, but I know this is just x and this is y, so I get x equals y, which means sigma g is injective. Okay, injective. Now let's prove that it's surjective. So let's let x be some element in x, and we want to prove that there's some other element in x which sigma g of that y equals x. So we see, we'll consider like y equals g inverse dotted with x. Okay, this is some element in x because I'm just taking this element g inverse, which is I'm trying to prove surjectivity of sigma g, so that's where the g inverse is coming from, and I'm acting on x. I want to analyze what sigma g of y is. Well, this is equal to g dotted with y but y is g inverse dotted with x, so this is g dot g inverse dotted with x, and once again I can group the g and g inverse, and then I just get x. This implies that, as we wanted, sigma g is surjective because I can take any element, find something in the set, and sigma g of that thing will send to x. So this proves surjectivity. And thus, sigma g going from x to x is bijective. So sigma g is a permutation of the set x. Okay, great. Now we still need to prove that rho is actually a homomorphism. Hopefully this is not too hard. So let g1 and g2 be two elements in our group. And if you remember the homomorphism rule from the last episode, we want to show that rho of g1 times g2 equals rho of g1 times rho of g2. Okay, well, we see rho of g1 times g2 is going to equal sigma of g1 g2. Now let's just analyze how this function behaves. Well, we see sigma g1 g2 of x is going to equal g1 times g2, then this applied to x. But using our action law, we can separate this parenthesis into g1 times g2 applied to x. But we know that this is really like saying sigma of g1 of g2 dotted x, but g2 dotted with x is the same as sigma g2. So sigma, this is really the same as sigma g1 of sigma g2 of x. And finally, this is really the same as saying rho of g1 composed with rho of g2, which is, of course, the group law in Sx, which is exactly what we wanted from the beginning. So we get that rho is a homomorphism. And so the definition I gave of it being a, quote, the action homomorphism actually makes sense. The reason I call it such, the action homomorphism, action homomorphism is because really all the stuff that's described by the action is also perfectly just described by this homomorphism rho. It describes everything that you need. So if you're given rho, you can fully understand the action, and if you're given the action, you can fully understand this homomorphism. Okay. One note, if you're confused about this whole SX business, if X is finite, like it's a finite set, then we get that Sx is just equivalent to Sn, where n is just the size of the set X. Because permuting a set X with n elements is really just the same as permuting the numbers 1 through n. Because you can think of X as being x1, x2, all the way to xn, and really you can just think of this as being 1, 2, all the way to n. Okay. A couple more definitions that will hopefully build us up to Cayley's theorem. Definition: the kernel of a group action G acting on X is the kernel of its action homomorphism. So what this implies is we know the kernel of a homomorphism, we define that. So really this is just describing the kernel of rho, which equals those elements G and G, such that sigma G is the identity. Which also means that it's those elements G and G, because the identity is just everything that sends the thing to itself, such that G dot X equals X for all X in X. A lot of X's. So you can think of it as like those elements that basically fix everything in your set. So you should already know that the identity in G is in the kernel. And so it's a helpful idea, you might think, is when are there other elements outside the identity, and when is there only the identity? So basically, that leads to its own definition, which is something called a faithful group action. An action G on X is faithful if its kernel is just the identity in G. Or this is equivalent to saying that the kernel of rho is just equal to 1. And if you remember from last time, when we proved the injective homomorphism theorem, when the kernel is just the identity, this is equivalent to saying that rho is injective. So when I think of a faithful group action, I'm really thinking of this thing, which is rho is injective, because this is kind of like the most useful thing you can get out of a faithful action. I also think the term faithful is very funny to have. It seems kind of arbitrary. Anyways, let's try to prove some things that you can get from faithful group actions. Let's prove a quick lemma first. If G, a group G, acts faithfully on X, set X, then G is isomorphic to a subgroup of Sx. Okay. Maybe if you've been following along with the definitions very carefully, this lemma shouldn't be too hard to prove, but let's do it together. Should be pretty quick. So let's consider our action homomorphism rho from G to Sx. And since G acts faithfully on X, this is an injective homomorphism. Now consider the subgroup image of rho. Remember, we proved that the imaging kernel of a homomorphism is a subgroup. Image of rho in Sx. We see that if we kind of just restrict rho, instead of going from G to Sx, if we just think of going from G to image of rho, well then, this is also surjective. Because, well, by definition, that's just the definition of the image. If it goes from G to image, it's gotta be surjective. And that means that rho is bijective and thus an isomorphism. Thus, rho is an isomorphism of G and image of rho. And that proves exactly what we wanted, which is that G is isomorphic to a subgroup of Sx, namely that subgroup being the image of rho. Okay. Finally, this should be enough to prove the big theorem for today, which is Cayley's theorem. Okay. Which says, at least how I'm going to write it, you can generalize this, but we're going to stick with just finite groups. Every finite group G is isomorphic to a subgroup of Sn, where n is the size of G. Okay, let's prove this. And note this is distinct to what we proved above, which said that if you have G acting faithfully on a set X, you get this. And this is saying every group G is isomorphic to a subgroup of Sn. So what we want to prove is that every finite group has a faithful group action. Okay. So let's consider a group action of G acting on itself. And it's going to be by what's called left multiplication, where G.H equals GH. Kind of how you imagine that, like naturally. And so you can think of this as left multiplication. My group element G acting on another element H, it's just multiplying G on the left of H. So let's prove that this is actually a group action. We see for all H and G, the identity acting on H is just H, because that's just the definition of the identity. 1.H is H. So that satisfies that law. And then for all G1 and G2 and G, and we also have, as we're thinking about our set, H and G, we get G1 of G2.H is going to equal G1, and then this is, I'm thinking as the group multiplication, G2H. But since groups have associativity, this is the same as G1, G2.H. And this is just, exactly how we want it. So that proves that group action law. So this is a group action. Namely, it's one from a group to itself. And so we can analyze what the action homomorphism is. So specifically, if we want to prove it's faithful, we want to prove that the kernel of rho is just the identity. So we're going to let G be an element in the kernel of rho. This rho being the action homomorphism from G to S sub G. Then we get, for all H and G, we get G acting on H should just be H. Okay, well I'm going to specifically choose H equals 1. This means G dot 1 equals 1. Okay, well G dot 1 is also equal to G times 1 in the group law, and the identity times any element is the same element, so this is G. But if we just finish this diagram, this shows that G equals 1, as we wanted. So if you have an element in the kernel, it's got to be the identity, which means rho is injective, so G acts faithfully on X. Or should I say G acts faithfully on itself, G, where we think of G as the set X here, is faithful. Thus, by our lemma, G is isomorphic to the image of rho, which is a subgroup of S sub n, where n equals the order of G. Because if we're thinking of our set, or G as our set X here, then we apply the lemma, which says we take the order of the set. Okay, great. And so this basically just proves Cayley's theorem. G is isomorphic to a subgroup of Sn. And so the main takeaway you should get, generally, is that you can think of groups or abstract groups as kind of just permuting elements in a way. In that, like, the way G kind of, like, let's say if I take an element G in a group, how it multiplies everything is kind of just like permuting all the group elements. The way G acts on other group elements is like permutations. Great. Okay. Now to end off, I wanted to give some exercises just for your own practice if you're watching this for review purposes. Okay. First one. I want you to determine the orbits and stabilizers of D3 acting on the equilateral triangle. So just take some elements in D3, find its orbit, and find its stabilizer if you're talking about elements in like the set here. Another question is, how many different orbits are there? I'm curious, how many distinct orbits? So this means not just like, oh, what's the orbit of the first vertice, what's the orbit of the second vertice. I want you to figure out how many different orbits are there. If I have one orbit and another, if they're disjoint in any way, then they're different. If they're not disjoint, then they're the same. Then try to generalize to D sub n acting on the n-gon. Okay. Second exercise, and hopefully this is something that we'll prove maybe in the next video, maybe in a video a little bit later, but it's good practice if you can prove it right now. Show that orbits are either disjoint or congruent or equal. Equal. What do I mean by that? Okay, said more rigorously, if G acts on a set X, let x and y be two elements in the set. Show if OX, so the orbit of x, intersected with the orbit of y is not the empty set. So there's something that's in both of them. Then OX equals OY. So this should not be immediately obvious that if there's anything in similar, then they've got to totally be exactly the same. What this also means is that basically you either have things being exactly the same or they're completely different with one another. Okay. And those are good exercises. I also mentioned another where you try to prove that the stabilizer of x is a subgroup. But hopefully that should be enough to get some good practice for group actions, orbits, stabilizers, and Cayley's theorem. Okay, thanks for watching.